Object-level geometric editing is a daily workflow in traditional digital content creation. You nudge a prop to fix a composition, rotate an actor to face the camera, scale something for emphasis, or remove a distraction. But when you try to do this with generative video models, it falls apart. The model either drifts from the intended path, breaks temporal coherence, or completely ignores geometry-dependent secondary effects like shadows, reflections, and occlusions. Existing approaches try to fix this with two main strategies, and both have serious flaws. The first relies on text prompts, 2D masks, or point tracks. These are convenient, but they don't explicitly constrain the target object's three-dimensional state. The model is left guessing, which leads to under-execution or mis-execution of the edit. The second strategy lifts the edit into explicit 3D space by reconstructing a per-video proxy, editing in that space, and then re-rendering. But per-video reconstruction is computationally brutal, brittle under complex motion, and prone to error propagation. If your proxy drifts or misaligns for even a few frames, that error cascades directly into the final output. What we actually need is a way to specify the target object's three-dimensional state change unambiguously, while letting a generative model learn how to execute that change and update its visual consequences consistently. That is exactly what GIV, or geometry-instructed video editing, delivers. Instead of reconstructing an entire scene or relying on ambiguous 2D controls, GIV represents edits as transitions between pre-edit and post-edit object states, guided by two lightweight, video-aligned geometry streams. The first stream is the depth box. It encodes the target object's coarse three-dimensional placement and spatial extent in camera coordinates. We do this by projecting a 3D-oriented bounding box onto a canvas and rasterizing it using a Z-buffer. For every covered pixel, we write the nearest surface depth and normalize it to a consistent range. This gives the model explicit spatial grounding. The second stream is the orientation box. It encodes the object's heading in an appearance-agnostic way. We render the projected 3D box using fixed, canonical RGB colors for each of the 6 faces. This creates an anisotropic orientation cue that tells the model which way the object is facing, without leaking any texture or identity information. Together, these streams define the edit implicitly. The model doesn't need a separate label saying rotation or translation. It just sees the difference between the pre-edit state and the post-edit state. Object removal is just an empty post-edit stream. Duplication is multiple instances rasterized into the post-edit streams, with occlusions handled automatically by the Z-buffer. This object state formulation gives us a single, unified control format for 6 different DCC-style operators. But defining the edit is only half the battle. The architecture needs to process these geometry streams alongside the source video, without losing spatiotemporal correspondence. GIV uses a conditional latent video diffusion transformer. The source video and the 4 geometry instruction streams are encoded by a shared video, VAE, into compact spatiotemporal latents. These are flattened into token sequences and concatenated into a single input: the noisy target latent, the source video tokens, the pre-edit geometry tokens, and the post-edit geometry tokens. Here is where a subtle but critical architectural detail comes into play. If you just concatenate these streams, rotary positional encoding breaks down. The transformer assigns independent positional indices to each block, so tokens at the exact same spatiotemporal location across different streams end up with completely different positional embeddings. The model loses the ability to compare the source frame with its corresponding geometry mask. GIV solves this with row P state alignment. We tie the row P indices across all streams to a shared latent grid coordinate. Then, to distinguish what's input versus what's output, we apply a constant state offset. Source state tokens and pre-edit geometry tokens receive an additional offset, while target state tokens and post-edit geometry tokens stay at 0. This preserves exact spatiotemporal correspondence while giving the transformer a clear semantic signal about which tokens represent the original content and which represent the intended edit. Of course, a model like this requires paired supervision. You can't train it to isolate a geometric edit using real-world footage, because motion, camera movement, lighting changes, and scene dynamics are all entangled. To get clean supervision, GIV uses a procedural data synthesis pipeline built in Unreal Engine. The pipeline samples scenes, target assets, camera trajectories, and edit programs. The engine executes the edit program while holding everything else fixed. Because it uses physically based rendering, geometry-dependent effects update naturally. When you translate an object, the shadow shifts correctly. When you scale it, the reflection stretches appropriately. Occlusions resolve automatically. This generates GIV data, a dataset of over 200,000 paired clips across 6 operators. It teaches the diffusion model exactly how pre- and post-geometry instructions map to executable, physically consistent edits. At inference time, you don't need an engine or per-video optimization. The system takes your input video, uses SAM2 to extract a temporally consistent object mask, and leverages G4D to estimate monocular depth and camera poses. From that, it fits a 3D bounding box trajectory. Instead of trying to estimate unstable per-frame orientation, the user simply specifies a reference heading in one frame. The system propagates that anchor through the recovered camera poses and box trajectory, rasterizes it into the same depth and orientation streams used during training, and feeds it directly into the model. The geometry instructions are fixed, tokenized, and conditioned on the diffusion transformer without any privileged buffers or iterative optimization. The results show exactly why this explicit geometric conditioning matters. On GiveBench, a curated benchmark of engine-rendered paired edits, Give consistently outperforms commercial general-purpose editors and specialized baselines across PSNR, SSIM, and LPIPS. The gains are most pronounced on strongly geometry-dependent tasks like scaling and translation, where unconstrained baselines tend to drift or underedit. On real-world videos, Give achieves the highest win rate in blinded user studies for perceived edit faithfulness. It preserves non-edited regions better, maintains object identity and motion without temporal drift, and crucially, updates secondary effects in a way that matches human expectations. Ablation studies confirm the necessity of each component. Removing the orientation box causes the model to fail on rotation tasks because the heading direction becomes underspecified. Removing the depth box degrades spatial grounding, hurting translation and scale accuracy. Skipping row P state alignment drops performance across all metrics because the transformer can no longer align corresponding tokens across streams. Using both streams together gives the model the exact combination of pose and placement cues it needs to execute precise 3D transformations. There is a trade-off, and it's worth being transparent about. Concatenating multiple geometry instruction streams with video tokens increases the transformer sequence length, which directly impacts computational efficiency and inference latency. Reducing this overhead through more compact geometric representations or structured conditioning mechanisms is a clear direction for future work. But for now, Give demonstrates that you don't need fragile per-video reconstruction or ambiguous 2D controls to achieve reliable, object-level 3D editing. By encoding geometric intent into lightweight, video-aligned state streams, and teaching a diffusion model how those states translate into physically consistent visual changes, we can finally bridge the gap between traditional DCC precision and generative video flexibility. This framework doesn't just edit pixels, it teaches the model how three-dimensional space works, and that changes what's possible with generative video.